Okay, so hi everyone. Thanks for joining today, and thanks to the conveners for the invitation to talk. So Fola asked me to talk a bit about metamorphic core complexes, which I haven't worked on in several years, so apologies that there won't be new research presented here. But that said, when I last worked on them, I focused primarily on what they tell us about crustal rheology. So today I'd like to focus on that aspect, and I'll be using my favorite metamorphic core complex, the Whipple Mountains, as a way to sort of illustrate some of the key features of MCCs, as I affectionately call them, and things we can learn about the crust from them. So I'll start with a brief overview of continental metamorphic core complexes as they occur specifically in the Basin and Range province in the Western US. I'll discuss some of the key characteristics that they exhibit with the Whipples as a sort of illustrative example, and also as one of the classic places in which some of these key characteristics about core complexes were first recognized. And then I'll summarize some of the findings into crustal rheology that core complexes reveal. So Basin and Range province, just for anyone who's unfamiliar, it defines much of the west central US Cordillera. It forms this sort of extensional corridor or band going from Idaho down through Nevada, Eastern California, Southern Arizona, and even into Baja California and mainland Mexico. And the province flanks the western side of the Colorado Plateau, which is much higher in elevation, and is thought to represent a sort of uplifted crustal or lithospheric welt that resisted much of the Western Cordilleran deformation, including the extensional deformation that encircles it on three sides. And the Basin and Range province is defined by this series of broadly north-south or sort of northeast-southwest trending mountain ranges and associated basins in between them. Many of these are sort of classic Horst and Graben or tilted fault block structures in which the ranges are flanked by high angle normal faults that accommodated a moderate amount of extension. But some of the ranges are instead defined by metamorphic core complexes that represent much more extreme amounts of crustal and lithospheric extension. But so those are the ones with letters on this right-hand map, including the Whipple Mountains, which is shown here as a W. So if we look at a lithospheric cross-section through sort of about 37 north latitude, we can see that the Basin and Range crustal and lithospheric thickness is estimated to be substantially thinned up to a factor of 2 in the most highly extended regions, with crustal thicknesses of less than about 35 kilometers and lithospheric thicknesses down to 50 to 70 from an original estimate of around 100 as still preserved within the Colorado Plateau. So to distinguish specifically what features define the continental metamorphic core complexes in the Basin Range, these are the sort of critical ingredients. They're typically domed or antiformal mountain ranges. They're quite different from the simple tilt blocks or Horst and Graben structures in the rest of the Basin Range. The domal mountain ranges are flanked by low angle normal faults known as detachment faults of sort of sub-regional to regional extent. In the hanging wall above these detachments, there are commonly very closely spaced brittle normal faults that extend the hanging wall rocks. And then the footwall of the detachment fault consists of a metamorphic core that progresses from low to higher metamorphic grade with increasing structural depth or distance from the detachment. To illustrate some of these features in more detail from the Whipple Mountains case, here's a satellite image of the range. It's very dramatic because the footwall rocks are light-colored mylanitic gneisses and Cretaceous plutons, and then the hanging wall rocks are very dark-colored tertiary basalts and associated sedimentary rocks, non-metamorphic. The range is domal in geometry with the highest part sort of in the center within the metamorphic core, forming this ridgeline here. And you can see that the hanging wall basalts form these sort of repeated northwest, southeast trending normal fault blocks. These normal faults are in the hanging wall of the detachment and formed at relatively high angles, but in some cases rotated to lower angles with progressive slip along the detachment. And the Whipple detachment itself forms the sort of flanks of the range, as well as several clip-in in these sort of blue and green colors throughout the center of the range as the fault sort of dips horizontally in the center and switches from east tipping on the east to west tipping on the west. Here's what the detachment fault looks like in this sort of north central part of the range. These are several clip-in, and you can see how the detachment is dipping shallowly east here, but then it starts to become even more shallow toward horizontal here, and then eventually farther toward the west, in the western side of the range, it's dipping toward the west. This is the desert, the Mojave Desert, so there's pretty much 100% exposure here, which is helpful for mapping this structure. A zoomed in view of those clip-in, the contact here is really very sharp. And in fact, it was initially mapped as an unconformity for that reason before people sort of recognized the possibility of detachment faulting. So now that brings me to the footwall rocks, and a key aspect of understanding what core complexes tell us about mid-crustal rheology lies in being able to interpret the structures that occur beneath the detachment within the detachment footwall. But before we sort of zoom in on the characteristics of the metamorphic core, it's helpful, I think, to first discuss a general model for how core complexes are interpreted to form. So I'm going to just sort of step through a very general model of core complex development. We envision that in the early stages of continental extension, the upper crust develops these high angle brittle faults that soul into a lower angle incipient detachment fault. The detachment fault itself, and then it is going to soul into a ductile middle crust that's accommodating extension, the same extension accommodated by brittle faulting in the upper crust, but in this case by distributed viscous deformation below the brittle ductile transition. And then as extension continues, the footwall of the detachment starts to become gradually exhumed as the upper plate is sort of progressively distended, and the detachment itself can become sort of warped through unloading and flexural isostatic response into lower angle orientations. The top of that original sort of distributed shear zone that was below the brittle ductile transition can get sort of captured by the detachment and exhumed and cooled very rapidly as it crosses through the BDT. But simultaneously, those mid-crustal rocks that are still remaining below the brittle ductile transition can be overprinted by more localized brittle ductile deformation along the sort of ductile roots or the ductile extension of the brittle crustal detachment fault. And then eventually a significant fraction of the middle crust gets exhumed and sort of quenched through this mechanism. And those fabrics that formed below the brittle ductile transition are only really overprinted in the upper crust right near the detachment by very discrete brittle upper crustal faulting. And so it's this tendency of metamorphic core complexes to exhibit more and more localized strain with time that allows us to use the footwalls of these complexes to sort of piece together the rheological structure, the stress conditions, the deformation mechanisms, in some cases, the shear zone thicknesses that characterize the middle crust and the brittle ductile transition in the continents. So if we reconstruct these different deformation phases for the Whipple core complex, it's one of fairly few core complexes that effectively preserves the whole mid-crustal section. In other words, we have a nearly complete transition from this sort of high temperature zone of distributed deformation at amphibolite facies conditions up to more localized deformation at green schist facies, a zone of distributed brittle deformation, and eventually very fine localized shear and sort of hydrothermal alteration associated with upper crustal strain. And I should note that these are not all sort of linearly laid out in a simple sequence along the fault, but these structures and their relative depths are reconstructed carefully from different outcrops throughout the Whipple Mountains and using their context with respect to the Whipple detachment. So to illustrate then some of these features in more detail from shallow to deep, here's another example of the detachment fault itself. Here it forms a silicified microbreccia ledge that resists erosion and sticks out very prominently in the landscape. You can see the sort of pinkish white footwall rocks and the black hanging wall basalts. If we zoom in on it, parts were originally sort of affectionately named the dance floor detachment by Greg Davis, who was one of the main people to map this region originally. And that's because of how polished and sort of slick the microbreccia ledge is in some places. And this slip surface tells us that at least at some stage, the deformation on the Whipple Fault, the last stage in particular, was dominated by extremely localized brittle slip in the upper crust. Furthermore, this stage of detachment deformation shows evidence for substantial hydrothermal alteration, including small amounts of copper and silver, enough that it briefly attracted the attention of Wyatt Earp, who, for Americans, he was sort of an infamous Wild West lawman that comes up in several movies, but also a real person. Tombstone, it's a great movie if you haven't seen it. But anyway, he came here and tried to prospect, and in the end, none of it was economical, but there was enough to kind of draw the attention of prospectors over the years. But then also importantly, isotopic data from these alteration products and from the microbreccia ledge indicate that the deformation took place during interaction with meteoric water. So it's clear the detachment fault during these stages of deformation was sort of sufficiently linked to the upper crust to allow meteoric water to permeate downward into it. So then that microbreccia ledge discretely crosscuts a more distributed zone of lower green schist facies brecciation and cataclasis that we think signifies that the fault exhibited a much wider brittle damage zone and fault core thickness at deeper sort of lower green schist facies crustal levels. So you can see that in this photograph that there's actually a sort of clear cutting off or cross-cutting relationship between this chlorite breccia and the indurated silicified microbreccia that defines the microbreccia ledge. The detachment is just basically right along that surface. Here's another example of a cataclysite, in this case with a very chlorite-rich matrix, but based on the very simple composition of the class, we can tell that this chlorite matrix is all essentially derived from the granitoid host rock. Here's an example of fault rock that appears to show several generations of progressive frictional slip and a sort of strain gradient from top to bottom, with breccias and oxidized sort of gouge matrix down to essentially ultracataclysites with no remaining class in the middle. And again, you can see from the class types that they're all granitoid in composition. And in fact, they're myelinitic in this case.
Whitney?
And several, yes.
You used about 12 minutes now.
Okay, thank you.
Sure.
Thanks. So then several of the features associated with this stage of deformation are indicative of seismic slip. This includes both true pseudotacholites that are very freshly preserved, as well as fluidized cataclysites. Sometimes the two of these even appear to occur together. So these types of brittle deformation features suggest that even this phase of brittle deformation along the detachment is more distributed at deeper crustal levels, and also that the Whipple Fault and the associated splays was seismogenic at depth, despite the fact that this was a fairly low angle structure. So then in addition to these chloritized breccia zones, we see several examples of localized brittle ductile shear zones, some of which are also associated with cataclysites. This example on the right, for instance, is this discrete brittle shear zone with pseudotacholites along it, but you can just see how it also has a sort of subtle ductile sigmoidal foliation around it, suggesting it began as a ductile shear zone and then terminated in relatively fast brittle slip. And the case on the left is a panel of dominantly brittle faults that cuts across earlier formed myelinitic gneisses. But in places such as here, where it's labeled PW 180, the discrete brittle section kind of gives way to a ductile shear zone that reorients the myelinitic fabric at lower temperature. So these types of features are interpreted as representing the ductile roots of the detachment fault as it soles downward below the brittle ductile transition during, for example, relatively fast strain rate pulses associated with earthquakes in the upper crust. Finally, then the majority of rocks within the Whipple footwall actually look like this. They consist of green schist and amphibolite facies, myelinites and myelinitic gneisses. In some cases, very classic sort of Augen gneiss with winged feldspar porphyr class and very strongly dynamically recrystallized quartz ribbons. So the sequence of preserved deformation mechanisms and depths gives us a nice descriptive view of what the continental brittle ductile transition generally looks like beneath major fault zones, at least extensional ones, and probably also by translation to things like strike slip faults as well. We can also examine this more quantitatively. This is work I did 10 years ago now during my PhD. But just to summarize, what we did was to look carefully at the microstructures associated with each of the ductile and ductile brittle deformation stages formed at different temperatures, and then use them to produce a crustal strength profile. And the temperatures came from titanium and quartz thermometry and also mineralogical constraints such as stability of biotite or chlorite. And then the stresses came from recrystallized grain size paleopiezometry. So for example, we quantified the stress temperature conditions associated with the sort of deep mid-crustal flow, essentially preserved by those Augen gneisses. Those would have really large recrystallized grains, which suggest low stresses and high temperature conditions. So they might represent a sort of point in stress depth space in the middle crust that's here. Then the localized deformation beneath the detachment at greenschist facies show more intermediate stresses and represent a point here. And then lastly, the structures showing sort of combined brittle ductile deformation have very finely recrystallized grain sizes, reflecting high stresses and low temperature conditions, representative of the rocks sort of crossing the brittle ductile transition. And so our results ultimately looked like this, and this represents a sort of naturally constrained strength profile through the middle crust. The diagram on the left shows the results in stress temperature space, which allows us to place constraints on the applicability of quartz flow laws. So in this case, we were able to demonstrate that this Hirth and others flow law was the experimental flow law that was most consistent with geologically reasonable strain rates. There's these values of 10 to the minus 12 to 10 to the minus 15, which are consistent also with estimated fault shear zone thicknesses from the Whipples and other core complexes. Whereas other experimental flow laws seem to really kind of overpredict the strength in the middle crust. And then on the right-hand diagram, we plotted the results in stress depth space and also plotted sort of Byerlee's law for normal faulting regime and hydrostatic pore fluid pressures. We were able to demonstrate that the stress we measure in the ductile rocks right at the brittle ductile transition are broadly consistent with Byerlee's law, which suggests that the crust around the Whipple fault was relatively strong. So this, again, was sort of a great advantage that the progressive deformation preserved in extensional environments allowed us to track the rheological progression of rocks through stress temperature space in a quantitative way. And then several sort of follow-up studies have been done since then that provide similar results from other tectonic settings. So to conclude, metamorphic core complexes provide a sort of snapshot of the middle crust at and around the brittle ductile transition. And then the observations of the structures within them tell us about faulting behavior in the upper crust and down into the middle crust where the faults interact with more distributed ductile shear zones. And quantitative analysis of stress and temperature from microstructures preserved from different structural levels within these core complexes allow us to sort of reconstruct stress depth profiles that then support the idea of a relatively strong middle crust or sort of a beak in the Christmas tree in continental regions. Thanks, and I'm happy to take questions.
Awesome. Thank you very much, Whitney. I'm now going to open the floor to questions from the audience. If you have a question, feel free to unmute your mic and speak.
Yep. Hi, Whitney. I've got a question, a few questions potentially. I guess, yeah, firstly, is there any evidence as to the time scales that these detachment faults are active over? And also is there some limit on the maximum amount of slip that can occur in the more extension?
Yeah, so there's the Whipple fault in particular has about 40 kilometers of displacement based on an offset dike swarm. And the timescales, at least, I mean, it's kind of tricky whether you relate the timing of extension preserved in the mylonites with slip on the active detachment, because I mentioned that we interpret kind of the early phases of deformation, including kind of incipient ductile deformation as the detachment is developing. But if you do that, it's about 15 million years. But Danny will probably talk in more detail, including probably about the Whipples, about the time constraints. But that's what it appears to have accommodated. From about 32 to about 15 or 16 MA is the age range that seems to show up for the Whipple fault in particular.
I've got another question. I mean, there's clearly evidence in the geology for seismic slip on the fault. Is there any evidence from like seismicity or geodesy for like current day slip on these detachment faults?
Yeah, I want to say in maybe Papua New Guinea would be a place where there's an active low angle detachment, and then there's definitely active low angle faults in Italy, in the Apennines, I believe. But it is kind of debated topic that there are certain groups that insist that A, these faults were never actually low angle, and B, if they another group that would argue that low angle faults don't produce earthquakes. But it's really clear from the structures that we see in the Whipple Fault that at least right around the damage zone of this fault there was seismogenesis associated with pseudotactylite generation. And I think there's evidence for that on many other normal faults as well.
Thanks.
Any other question from the audience? If there's none, I can ask one question. Whitney, so is there any way to distinguish brittle deformation that's associated with the younger normal faults, these typically the pin ones that often develop when detachment fault become too subhorizontal? Those are secondary normal faults. Is there any way to distinguish the deformation associated with those faults from the ones associated with the
yeah,
I mean, faults?
Yeah, you can, because especially because of the 100% exposure, you can see these low angle or these higher angle faults soul into the detachment. And, therefore the brittle deformation associated with them really only affects the hanging wall rocks. Whereas whenever you see, and they don't cut the detachment. So any brittle deformation you see below the detachment, you pretty much have to relate geometrically to the detachment itself. So I've never seen any of these high angle faults actually cross the detachment fault. There can be later structures unrelated to this context of extension, but those big faults that I showed photos of are always soling into the detachment itself and not cross-cutting it.
Good to know. Thanks.
Paula, excuse me, can I ask a question?
Yes, please go ahead.
Before you finish.
Yeah,
Hi,
go ahead.
Whitney.
Hey,
I know that you kind of like a lot of more looking more detail the quartz deformation in these zones. Have you looked at plagioclase and how they really contrast in the terms of the ductile deformation and strength?
Yeah,
if you could look some piezometer.
Yeah, one thing I actually have done is compare the recrystallized grain sizes and recalibrate piezometers partly based on these rocks, based on the recrystallization of plagioclase versus quartz. And the grain size is always smaller, so it tells you that the plagioclase is deforming by slightly higher stresses. It is a stronger mineral. It is one of the minerals that forms the augen and the augen gneiss. So it's definitely stronger, but the kind of justification, and of course it was simplified for 10 years ago when we did the work on quartz, was that in many places the quartz forms these interconnected ribbons. And so the simplification is that that's what's mainly controlling the stresses in the middle crust. But of course, if you numerically model the contribution from feldspars for different relative concentrations of feldspar, you will find different viscosities that don't correlate just with pure quartz. So it is a simplification.
I see. What about the amphibole? What you would say that he would be doing during this myelinization?
There's very little amphibole in these rocks. It occurs occasionally and it rotates and it doesn't accommodate plastic strain, but it's very uncommon in these granitoids. They're sort of mostly tonalitic in composition. So yeah, a few more mafic dikes around that are part of kind of the original gneissic terrain, not part of the Cretaceous in Pluton, have amphibole, but it's really quite uncommon.
I see. Okay. Thank you.
Sure.
Yeah, I do have one question for Whitney. It's a less important question I didn't ask. In the beginning of your talk, that you showed sort of like a simplified crustal cross-section of the Basin and Range, and it seemed to show like sort of cartoon style. It had quite a thick upper crust and then a really thin lower crust, but that seemed completely kind of counter to what you think would happen for the formation of a metamorphic core complex. I don't know if there's sort of more up-to-date constraints on the crustal structure or is there any comment on that? It just looked a bit strange. It was really early in the talk. There was kind of like you had the thick lithosphere in the area next to the Basin Range. Then the Basin Range had a sort of normal upper crust, then lower crust.
Yeah, I mean, I think part of it, well, so that is one model, and that's a relatively old one from 95, I think. I think it was called the CoreCorp or CoCorp cross-section. I can't remember the geophysical survey. But I think part of it is that you should envision that and superimpose on continental collision or subduction-related development of the severe hinterland. And so then, if you picture that the original crust should have been substantially thickened through orogenesis associated with Cordilleran subduction offshore, then that would have, meant that the crustal thickness gets much thinner. But then there's the issue that people debate where the lower crust, how it participates in this, and some of the models are kind of more a bit like Tibet type, where people envision lower crustal sort of extrusion toward the east, away from the core complex zones, such that that's how you actually remove it and get rid of it. And I don't feel like the core complexes, most of them don't exhume lower crust. There's a few in northern sort of Nevada, like the Snake Range Ruby Mountain complex, that has deeper conditions that show up, that people debate this and discuss more about lower crustal rheology and behavior, but the Whipples only goes to the middle crust. So I feel like I have a hard time commenting on it. But yeah, it's true. That's just one model for the crustal and lithospheric thickness, and then others, show dominantly crustal thinning and very little mantle, participation in the overall core complex development. So I think, yeah, there's different ideas about it.
Thanks.